given the choice between being right before lunch and right after lunch, I always go for right before lunch. Because then, like, everyone's really excited at the end of your talk instead of falling asleep in it. Because that's what I do after lunch. So, I have to apologize. I have a slightly hoarse voice. My kids were sick 3 weeks ago, and still I have a hoarse voice. And it didn't help that I've been speaking the past 4 days. So, here I am. This is 7 hardware hacks for 7 GBP, Great Britain pound. Is that how you abbreviate it? Did I get it wrong? BP? British pounds? Mm-hmm. What? £7, $7, $7.
Good boy.
What's that?
Good boy points.
Good boy points? Good boy points. 7 good boy points will get you a bunch of hardware hacks. So, let's get on with this. Whoops, where's my picture's not on here. I'm Joe FitzPatrick. I do hardware hacking and training, and I have been doing this for 6 years on my own. Prior to that, I worked at Intel, the company, not the community, and I was working on silicon debug, so all the CPUs that come off the line, figuring out why they don't work when they don't work, and how to make all of them faster. From that, I moved into product security. So I was doing desktop and server CPU pen testing, pre-release, pre-silicon, and post-silicon. I got bored of that and wanted to travel a lot more, so I decided to start teaching classes to a broader audience of people. So Gordon and Dominic and others have told me many times that I should come here to give a presentation for several years, and so I'm glad to actually be here finally. It just so happens I have a class this week in Edinburgh, so I have an excuse to be here. I was excited it happened to be the same week. So I'm looking up Abertay University. This is right off of the little search help thing that Google gives you, and I was pretty excited to see notable alumni. There I am, right at the beginning. This is before I grew my hair. I actually have a Google alert on my name, so I can see like when things pop up, and I get a lot of hits for members of Scottish Parliament and health ministers who have lots of things to say about organ donation and everything else. But it's kind of neat because, Joe FitzPatrick is always in the news. But what I'm going to talk about is hardware hacking and tools for hardware hacking. Anybody seen this before? What is it? Who loves a bus pirate? I hate the bus pirate. Can't stand it. So about 10 years ago or so when it came out, it was pretty cool. You could, for I think it's $35, I don't know what it is in your money, or what it'll be in your money in a month, because who knows what's going to happen. But for $35, you have this little device. It's got a microcontroller on it. This one right here is a USB to serial chip, and then right next to it, this is a PIC microcontroller. And that PIC microcontroller would basically speak all sorts of different protocols that you might want to speak. It could listen and tell you over a serial cable what's going on. It was designed so you wouldn't have to have any software on your computer. You could just use a serial terminal and talk to this thing. So, and at the time, it was pretty awesome. There was no other tool that would do similar things for even close to that price range. If you wanted to do anything fancy, looking at signals or observing things, you need something like this fancy Windows XP running logic analyzer, right? These things are, if you're a student at a university and you have an electronics lab, you might have access to one of these. But if you didn't, you had to beg your friends or find someone who had one at work or something else to get your hands on one of these devices. Because they cost, thousands, if not tens of thousands of pounds or euros or quid or dollars or whatever. But something on that order of magnitude. Probably even higher on Zimbabwe dollars. It was probably a few trillion Zimbabwe dollars. Anyway, recently there's been these new tools, these Salier logic analyzers, and this is about an inch and a half, 2 inches, or what's that? 5 centimeters on the side. These tiny little devices, they have a bunch of wires. These are logic analyzers that can hook up to your signals. So these things cost closer to about $100. Right? So we have a big difference in our tools, but still, $35 for a bus pirate, it's kind of the best way to go. Logic analyzers on benchtop didn't make sense. PC-based ones suddenly made things a whole lot more accessible. So I've been using this board for quite some time. This is made by Adafruit, and it's a company in the United States that builds these like hobby board things. What's important though is on top of here is the FT232H chip, right? And FT is the company name, FTDI. 232 comes from RS-232 because these things used to speak RS-232 and not much else. H, because this thing is the high-speed version. It can do more than just RS-232. It can do JTAG, it can do SPI, it can do all sorts of things. And we'll see that it can even sample and output data at up to 30 megabits per second, which is pretty awesome for a chip that costs, at least in the US, it costs $15. Who knows what it costs here? Maybe in a year you can get them here for only 15 euro. Oh, yeah. So anyway, I said 7 pounds though, or 7 good boy points, right? And that's a little bit more. But luckily, you can go to AliExpress, which is this warehouse of everything you ever wanted to not order from China, or everything you would want from China, but would hope to be in slightly better quality than you're actually going to get it. For $7.44, you can get these things, and like, at least for me in the United States, until about 6 months ago, there really wasn't a lot of duties and tariffs on stuff coming from China. I don't know if you follow the news, but there's this whole trade war thing going on, and like tariffs and all that crap. But you guys got your own news to deal with, so I understand. So 7 pounds, 7 good boy points, or $7, you can get a board. It's based on the same chip. And so when we talk about things that we're going to do, we're not dealing with the board. It doesn't matter whether it's purple or blue or red or anything else. We're going to use USB to talk directly to that chip, and use that chip to talk directly to wires, right? So I thought it'd be pretty cool since, like, I use this chip so much. I contacted FTDI. Their headquarters is in Glasgow. So I said, hey, I'm going to give a presentation at a university in Scotland, and I thought maybe you guys would donate a whole bunch of cables so I could give them out after the conference. And of course they said no. And I was like, okay, well, can you tell me the procedure, how I would request academic donations in the future? And suddenly that went down the right path, and someone said, oh, we can do that. We can send you some cables. They're like, yeah, that'd be great. Like, I live in Oregon, in Portland, which is literally 20 minutes from their US headquarters. And here, you're an hour from their, worldwide headquarters. We have to figure out how to get these cables, right? Weeks go by, right? I left, and I've been in the UK for the past week, so, like, I can't get them at home. Monday, they finally get in touch with me, like, hey, sorry, we dropped the ball on this. You still want those cables? I'm like, sure. You can send them right to the university. I'm like, okay, well, we'll figure that out. And they go back and forth for 3 days. So yesterday, they shipped a whole bunch of cables overnight, supposedly to here, but they were supposed to arrive at noon. I have no idea where they're going to end up, if they're going to make it here. Last I looked this morning, they were in Stansted Airport. They were also kind enough to use my FedEx account number to ship those cables overnight from right down the street from my house. So, we could call this a sales pitch for FTDI because I'm telling you how to use their boards. We could thank them for donating those cables, and it is really nice of them. But, whatever. This is being recorded. Maybe they won't give me them next time and save me the time. So I said 7. Should I adjust the microphone? Is the feedback okay? We good? Okay. And here are the 7 scenarios I'm going to walk through. So using FTDI LA for a logic analyzer with SIGROC. We're going to use a UART with console access to go directly talk to a single board computer. And then we'll use OpenOCD, another tool that supports this FT232 chip, to do JTAG control and manipulate the live running system. Then we'll use Flash ROM for 2 things. The first is to dump the firmware off of a system. By dumping the firmware, we can get a copy of all the code running on it. We can do some offline analysis. If we got fancy, we can go and manipulate those files and then flash them back to the same system and boot it up backdoored or with root shells or whatever, fun stuff you want to put on there. And then last 2 bits, we've got using it to communicate I2C. I2C is a protocol that's used for configuration of lots of tiny chips. Actually, the FTDI itself uses I2C to configure itself. And then bit banging crafted packets, talking about how to use this as like a raw output device where we can tell what 1s and 0s we want to come out and when. So I'm going to take a sip of water since my voice is going great. This is a hoarse voice. This isn't an American accent, in case you were wondering. So first, we've got the FTDI-LA. So FTDI-LA is a driver for SIGROC. SIGROC is an open source logic analyzer platform. So I mentioned before, we have those Salient logic analyzers, and they're pretty cool. The problem is, as I'm going to rant about more companies, they have an awesome logic analyzer you could get for $60 US with a student discount. It was 4 channels. It did most of the basic stuff. It was really solid, really reliable, and it had pretty easy to use software. So what they do, they canceled that product. And then they doubled the price of all their other products. So their cheapest one is $400. So how many of you have $400 to buy a logic analyzer right now? So it just bothers me because I'm trying to get people to start doing this stuff. So FTDI-LA is a driver to use this FTDI board as a logic analyzer. So what I've done here is I got my board. I don't have the $7 one. I have these because I have just tons of these. Actually, I have about 30 of them with me for the classes I'm teaching this week. And we hook up a bunch of wires to this header on the Raspberry Pi here. So I chose the Raspberry Pi just because, again, I have a bunch of them because I use it for classes. What we want to do is we want to listen to what those signals are doing, right? So it's an electrical observation tool. And what we can do with the software is we tell it to connect to this FTDI 232H. And then we go and tell it to capture 1 million samples. This is actually the previous capture I did. What we really want to do is capture a few million samples at about 1 megahertz, right? So we click run, it'll go and capture data. So we'll get a whole bunch of ones and zeros. If we look closer at this data, we'll see that the data goes up and down and up and down. That's data being spit out on these pins. So now we can use the logic analyzer to interpret it, figure out what it's doing, what it's communicating, what it's saying. Right? Now this program is PulseView. PulseView is the front end, the graphical front end to SIGROC. So we can do this all on the command line if you're really, sharp and like command lines. Or we can do it with a nice graphical display. We can then go and use this option over here. These are protocol decoders, right? So it's just a matter of details about what these signals are doing. If we know that we have a serial protocol, we can then go and apply a protocol decoder and tell it we want to decode the data here. We want to interpret the ones and zeros and ones and turn them into bytes, right? So right now we have the ability to measure a signal, observe it, understand more about it. This is great for finding ports that a chip is communicating on. This is great for listening between 2 chips that are communicating to each other. It's just really handy to do. So, another sip of water. I should, drink. We got one. I'm already drugged up, so don't worry. Cold medicine, not anything else. I should have 7 shots of whiskey, right? For the 7, And that's good to clear your throat too, isn't it? Yeah. I don't like whiskey though, sorry. So, serial console. So we, on that Raspberry Pi, were just poking around at a few wires, and it just so happens that this is UART. This is a serial communication where the Raspberry Pi is telling us about the boot process. It's giving us all the things that happen as it loads the kernel, loads drivers, and then it shows us a prompt where we can do stuff. So we're going to use the exact same board, and we're just going to use it. Oh, I didn't even put the command line here. We're going to use it using a tool called Screen. Has anybody ever used Screen before? Okay. Has anybody ever used Screen to talk to a serial cable before? Okay, good. Apparently Screen also has other uses too. This was news to me a few years ago. I had been using it for over a decade to talk to serial cables, and then I found out it has other purposes where you can have multiple terminals and all that fun stuff. But anyway, Screen. And what we do is we need to tell it to talk to the cable, so we call it dev, this is on the Linux system, TTY USB 0. And we also have to tell it the speed we want to talk. We don't know with UART what speed it's talking until we sit there and look at it with a logic analyzer, which we just did. So we just happen to know that this is 115,200 bits per second, right? We do that, and suddenly we get data. We get text running right on our screen. So again, sometimes you'll do this, and you'll end up straight to... I originally wanted to do a bunch of demos with this, but then I realized that my time was kind of limited, so I just screenshots instead. So now I'm thinking like, if I just pulled it out and figured out how to get that document camera up, but I'm not going to do that because then you'll all be bored watching me try and make wires work. But hardware is actually easy. It's not that hard. Just Ask Graham later. So what will happen is we'll run this, and it'll give us all this stuff going on, and then finally at the very end, it may or may not give us a prompt to log in, which is cut off on the bottom of this. So when we want to log in, sometimes it'll say, hey, you're root. You get this little pound sign, and you get a prompt or a colon or a slash or something, and it tells you, hey, you're root, you do whatever you want, all these commands are available to you, it's fun times. Other times, it's really obnoxious and it logs you in as a different user. Sometimes it's really, really annoying, and it asks you for a password. Like, what do you do there? Like, I don't have a password. I mean, you could sit there and write a script that'll try every password, but that's no fun. So we might have to find another scenario, another way to get into a system like that. One option is JTAG. So who's used JTAG before? Right? So JTAG is the Joint Test Action Group, right? So this is where all the joint testers get together for some action, where they talk about how they want to test their board. So it's an IEEE standard. It's designed in the 80s for board testing to make sure your boards are hooked up together. But every device had a tap in it, a test access port, to use this board test feature. So what manufacturers did of CPUs is said, hey, we want to be able to debug our CPU as well. Let's add those commands to this interface. So out comes this tool, OpenOCD. So that's not OCD like you're thinking. It's on-chip debugger, right? So, and it's open source, which means that if you want to read any documentation to understand how it works at all, you have no choice but to read the source code, which is written in C, sort of. So anyway, OpenOCD looks familiar. We've got the same board, USB cable going to the system. I have this little wiring harness. I did hook up the wires to different pins this time, right? Every device has different debug pins that are dedicated, and I actually had to cheat a little on this one. I had to go in there and change some software configurations to enable JTAG, right? JTAG is a debug feature. We don't usually use it in normal operation. We only use it when we're going to test the chip. So manufacturers, they really, when you're designing a chip, it's more expensive to have a pin than it is to have more function inside the silicon. So they try to minimize the number of pins. So they have multi-purpose pins. So we told those multi-purpose pins to go back into JTAG mode so we could go and mess with our system. Next, there we go. So OpenOCD is the tool we're going to use. We use a -f command to include a file. And the first file we have is ft232h.cfg. This is a configuration file that tells us where to find this FTDI board, what vendor or device ID it looks like, and just some details about how we're using it. And next we have Raspberry Pi.cfg. This is a configuration file that tells us that we have an ARM 1176 processor, and it has a certain amount of memory and other features. So we're telling OpenOCD details about our part. We start OpenOCD, it starts up our adapter, looks around, finds a device. Device is identified with a code, it's recognized as a Broadcom part. Just like we were talking before, when we were talking about the less expensive and more expensive FT232 boards, they're all the same, they all have the same chip on them, right? When it comes down to coding and working with it, what we care about is the manufacturer of the silicon. Same thing comes when we're talking about using JTAG, right? We're not talking to a Raspberry Pi with JTAG. We're talking to a Broadcom ARM 1176 processor. Doesn't matter whether it's on a Raspberry Pi or a Pi Zero or inside of a flip phone from the 90s, which is where that processor belongs. Anyway, we find our breakpoints or watch points, so we have our ability to go and debug our part now. How many of you have used GDB before? Right? Have you used GDB to debug a process? Right? So you attach to a process, you use GDB, you can, X10i, show 10 instructions at the program counter and look at the contents of memory. Neat stuff like that. Well, that's exactly how OpenOCD works. You can start up GDB, instead of telling it to attach to a PID process ID number, you tell it to attach to OpenOCD. And then you're directly using your hardware to go and debug this. You're using your JTAG adapter to debug the hardware on this little board. Another drink. Cheers. So next, flash ROM, dumping firmware. So people talk about dumping firmware and say, oh yeah, just dump the firmware and we'll deal with it later. Just grab the firmware. And really, if you're a software person, your goal is to get code to look at, right? If you're a software person looking at an IoT device or a network adapter or a webcam or anything like that, once you get the firmware off of that, you've taken this hardware issue and turned it into a software issue, right? So I'm a hardware person. That means when it's a software problem, it's someone else's problem. So I love getting firmware off of devices and handing it to someone else to deal with. So flash ROM is a pretty pervasive tool. It's very common and supported on most distributions. It can read flash using about like 30 different pieces of hardware. So there is the FT232H we're going to use. We've also got a handful of other devices made by commercial companies like name is SF600. What is it? Debugging. Debugging is this a few $100 device that does basically the same thing. It lets you talk SPI to a flash chip. So we'll use flash ROM in this case. We'll wire up. This is a Wi-Fi router I've been dealing with. And we have a CPU here. It has memory. And right over here, you can even see my green. Oh, change to red. Right here, we've got a flash chip. It's a little 8-pin chip. It stores 8 megabytes of data. But that 8 megabytes of data is enough to store a bootloader, a kernel, a root file system, and have a little extra space to spare for using modified files. So what we'll do is we'll clip to the pins of that chip, right? We can look for the data sheet of that chip to tell us which pins to clip to. And again, same board, same USB cable to our system. And we just have to use the right invocation to make magic happen. What we're telling here, we have flash ROM is the program. We're telling it to use a specific programmer, and it's the FT2232_SPI programmer. So FTDI actually makes a whole bunch of different chips. They make the 2232, the 4232, and the 232. And it just matters how many ports they have on them. So I use the 232H. It's the cheapest and smallest. It only has one port. The 2232H has basically 2 of those chips sandwiched onto one piece of silicon, and the 4 has 4 of them. I don't know why you need a USB cable with 4 serial ports, but hey, someone must. Actually, I can think of a few good reasons, but anyway. And then what we tell it to do, we have to tell it what type, because again, we have variants of this chip. They all use a similar driver. We need to clarify that it's the 232H version. And then we want to read, so we do the -R and the file we want to write it to. Okay? Flash ROM goes, and this doesn't happen the first time ever, right? It goes, it says, detected a part. We found a WinBond flash chip, and we're going to dump it. We're going to read flash, and we're done. This takes a few minutes. When it doesn't work, it gives you all sorts of errors. Sometimes it says, we found a flash chip, we don't know what it is. Sometimes it says, we didn't find a flash chip, but we're going to pretend there's a flash chip there and give you a lot of cryptic error messages, but not really tell you what's going on. Again, open source tools. If you want to learn more about how it works, you can either read the source code or do what I do and hook up your logic analyzer to it while it works so you can understand what the heck it's doing, because code is hard to read. Logic analyzers, for me, are easier to read. Anyway, we did it. We're done. We got our SPI dump. Yahoo. But again, I said once we get firmware, we hand it off to software people and they can deal with it. But it's still not in that nice form yet. So what we can use is a tool called binwalk. Right? This is a great tool. Basically, if you ever use the file command, file looks at the beginning of a file and says, this looks like a PDF or a zip or a JPEG or a text file or code or an ELF. And binwalk basically walks through an entire file and looks for the beginning of files at different intermediate spots in that file. So it's going to walk through this and say, I found a document header, HTML document footer, so maybe I found an HTML file in there. I found a copyright string, because people are usually interested in those. Those usually come with kernels, right? We have this header image, and we're going to break it down and say, this is a Linux MIPS kernel that's going to follow here. And here we have LZMA compressed data. Knowing that it's LZMA compressed data means that this tool knows how to decompress it. So there we go. We got the kernel. We can decompress the kernel, and we can go and walk through it and look at all the details in it. Sorry. It's a good thing I'm not handing out cables, because then I have to put my hands in them. So LZMA compressed kernel. We also have a couple other things down here. We have a SquashFS and a JFFS2 file system. These are the file systems that hold all the details, all the extra files in addition to the kernel to make the system run. What I didn't show here is there's a -E option. Any guesses? Extract. So that'll go and extract all this cool stuff that it found. Isn't that handy? So if we go and extract these files, what I chose to do is extract the... this time is off. That's why I'm... Sorry. The clock on here is 10 minutes fast, but it's okay, because we're doing good. -E extracts it. What I'm going to do is I'm going to look at the SquashFS file system. This is going to be a full root file system. So it'll have an Etsy directory, and inside that Etsy directory is going to have all the useful files, all the fancy files that we want to modify to go and give ourselves privileges on this. So who's familiar with Linux and knows what files we can modify to give ourselves privileges? Any guesses in the back of the room? Where are passwords stored on a Linux system? Right, so there's Etsy password, which stores user information, and Etsy shadow, which stores the hashed passwords. We have access to those files. If we wanted to, we could go and we can crack hashes, but that's no fun. That's for people who, don't want to mine Bitcoin anymore. We're going to go, we can go and we can modify and put our own hash in there, recompress it, and send it back. We can go into the password file and go and say, oh, there's user. I know how to log in as user, but change user ID to 0. And then when you log in as user, you're root. But what we're going to do is we're going to look at this init tab. Basically, a whole bunch of initialization programs get run. This is OpenWRT, which is a distribution of Linux catered specifically for Wi-Fi routers. And right here, when it's asked for a console, I'm going to run bin login-f user. I'm like, let's change that. Let's change that to -f root. Okay? So wouldn't it be nice to just turn it on, plug it in, and ask for a console? Here is your root console. Sounds like a good deal, right? So then what we can do is we can take this file system and we use a tool called make SquashFS. Right? So SquashFS is a compressed file system. We can't just mount it. We have to go and extract files from it and then pack them up. It's kind of like zipping a file. You have a zipped copy of your file system. So we'll use make SquashFS, and we'll use that to rebuild a firmware image that we can flash back to our device with FlashROM. There are other tools than FlashROM to do this. And actually those other tools are, in my opinion, a little bit better than FlashROM. But everybody seems to want to use FlashROM because everybody knows how to use it. I don't know. I end up going back to FlashROM all the time because it's always there. It's always on every Linux distribution, and every other custom tool I come up with, I have to support, and I don't want to support custom tools. Echo. So let's talk about writing firmware. It's really tough. Basically, we take the same exact command line and we change the R to a W. Pretty cool, right? Same wiring, same hookups, same everything. We've just taken a dump, we've gone and modified it, changed a couple bits, we repacked it, and now we're flashing it right back to the same device. Okay? So looking back at what it looked like before, where'd it go? There it is. Same setup. Let me clear up some of my clutter so we can look close. If you want to look more at the system, you'll notice there are some weird wires. I did those. They didn't come. That's not factory. Although I've seen similar factory-type jobs in sketchy hardware. So what happens is this CPU always wants to talk to that flash chip, right? So in order to make all this happen, we have to tell the CPU to shut the heck up, right? So what do? We want to tell it to reset and just stay resetting and keep resetting until it's time. Sometimes you're lucky to get a reset button. You just hold that down the whole time. Well, this system didn't have that. So what I did is I looked at this chip. I found out that this wire right here is the reset wire, and I hooked that all the way up over here to a jumper where I pulled it to ground, right? And, it's a little, I put crazy glue, hot glue on there to hold it in place, because if you're going to do something more than once, you should do it right? So hot glue, that's the right way to do it, right? Way better than duct tape. And I also, if you're ever tempted, don't use crazy glue. It just makes a mess of everything. The worst part is crazy glue will get underneath these little pins, and then the next time you try to use your little probe clips to clip onto them, it won't be able to get around the back of them, and they will fall off. So don't use crazy glue. Hot glue, okay, for hack jobs. Anyway, we flash it back. This device has a serial port right there. We can hook up our FTDI board to talk to that. We watch the system boot, and we can see, were we successful? Did we end up with a root shell? Hopefully it did. Sound good so far? Cool. Excuse me. Next, come on. Okay. Flash while writing with the W. Now, modifying I2C configuration. So I don't actually have the photos with me here because all of my I2C stuff is sitting on my desk at home in Oregon. So I didn't have any surveillance cameras that I could get a good shot. So what we have is I2C configuration, and if we look back at this device, we're going to look very closely at the FTDI board, right? And we see there's this big chip here. That's the FTDI board. We have some a crystal that gives it a frequency, an oscillator. We've got a couple LEDs over here, and then we've got this other black chip, right? If we look in, it's got 6 pins. It does something, right? This is a serial EEPROM. That's pretty pudgy writing. Sorry. So we've got a serial EEPROM. This is a little chip that holds a couple bytes of storage. So that flash chip we talked about before was about 8 megabytes. This is like 128 bytes. That's all. What happens is when this chip powers on, it goes and talks to that and says, hey, who am I? And this chip says, oh, you are a CJMCU FT232H. Or if you're fancy, it says you are an Adafruit FT232H. So when you pop it up on the screen, when you load it, the driver shows up and says you have attached an FT232H. It gives the name of the manufacturer that's using it. The reason we have something like that is because if we remember this bus pirate, like this bus pirate used a very similar chip. That's actually the FT232R, right? That means it's slow. It can't do anything but UART. But when we plug the bus pirate in, it says, hey, I'm a bus pirate. Sounds good, right? The way it says, hey, I'm a bus pirate, there's a little flash chip right there that tells it it's a bus pirate, right? So if you're a manufacturer of, like, I don't know, a USB microphone or something, I don't know, whatever. And now you would give me an example. Dominic, you're on the spot. USB device with an FT232H. So like a little radio dongle for like a toy, right? You would speak USB to the serial cable, and that serial cable, serial protocol to the actual hardware. But you would want this device to say, hey, I'm a Mattel, or I'm a, Sony, or I'm some other brand device. I don't want to say I'm not an FTDI device. I am a branded device. Anyway, the point being, we can go and speak the protocol that this speaks. We've got, this tool, this library called libmpsse, right? Which is an abbreviation, an acronym for something. I don't remember what, I never do. But it's basically the FTDI's high-speed interface where you can go and tell what pins you want to do whenever you want them to do it. So with this, we say, oh, we're going to have an I/O device, and we're going to set some pins high and some pins low. We can choose, wait, this is the wrong one. Sorry. There we go. I'm talking to the wrong slide. I had them out of order. So we have MPSSE, and we have a bunch of I2C commands that we can do. We can have an acknowledgement. We can write bits. We can get acknowledgements, and we can read bits, right? So we basically have an API built into this. And it's funny, this tool, libmpsse, it's a bunch of wrappers and an API. It's written by the same guy who writes binwalk. So he really knows his stuff. Craig Hefner, you should follow him. He's like, I think he's at devttys0 on Twitter, so you should follow him. He's smart. And what we'll do is we'll say, hey, we're gonna talk I2C at 400 kilohertz, and let's go start writing data to that or reading data from it. We can then communicate with that chip. We can change the configuration on that chip, and suddenly we turn our whatever we had, our knockoff CMJMCU FT232H, we can pretend it's an Adafruit. We can pretend it is any other manufacturer that makes a board based on the same chip. And last thing that I mentioned was bit banging a custom protocol. Who knows what bit banging is? So up to this point, I've been talking about existing protocols. I talked about JTAG, I talked about UART, I talked about SPI and I2C. You can go and look for timing diagrams and ideal scenarios. You can find chips that support these protocols. But sometimes you encounter protocols that are different. Rarely, but you do. And usually when you encounter them, it's because someone did a poor design job. But anyway, sometimes you want to speak a different protocol. Or sometimes you want to speak a protocol differently. So if you wanted to mess with the timing on your SPI interface, if you wanted to start doing maybe even glitching or something like that to try and get readouts from a flash device, right? You would want to have very fine-grained control for when your signals went to 1 or 0 or anything else. So what we can do is we can use bit bang mode, right? And what we do is we want GPIO mode. That's general purpose input output. So basically we have a bunch of pins on this device. We can tell any one of them to be an input or an output. And if it's an output, we can tell it to be a 1 or a 0, a high voltage or a low voltage, right? So as a great wise friend of mine once said, once you can turn on and off an LED in hardware, you can do pretty much everything, right? So, so basically, it's all a matter of timing when you turn those on, bits on and off. So the combination of setting your pin states high and setting your pin states low, pin high and pin low, and doing it with precise timing, that's all it comes down to, right? Once you have the ability to do this in software, you have a world of protocols at your disposal. Almost done. So, here we go. Seven scenarios we went through. 7 things you can do with a $15 or 7 good boy board, or maybe a few years a €15 board. I don't know. You can use a logic analyzer with the software SIGROC. You can use UART console access. You can use it as a JTAG controller to access debug functionality of a chip. Right? We can use firmware dumping and writing, reading and writing, to manipulate a system. And we can also do some configuration, messing with configuration of various devices. And if you need to, you can always craft your own custom protocol from scratch in software very tediously. Of course, you're not doing this with just a piece of hardware. There's software that supports all this. So these are the tools that I use on a regular basis. I find them to be quite reliable, even if I have my complaints about them. Again, SIGROC, open source logic analyzer framework. PulseView is its graphical front end. Screen is this multi-purpose Swiss Army knife of consoles. It can speak to your serial cable. It can speak to whatever brand of serial cable or your built-in UARTs or anything else. OpenOCD is another open source tool. It does your on-chip debugging. It lets you control the debugger with JTAG or even SWD, single wire debug. FlashROM is the flash reading writing Swiss Army knife. It works with this bootboard. It works with commercial tools. You can even use FlashROM on your laptop to read the BIOS off of your own laptop or PC or everything else. Binwalk is a great tool once you've got that firmware image to go and break it down into pieces so that you can make sense of it, so you can hand off the software parts to the software people, or you can just mess around with text files if that's all your skills are, like mine. And lastly, there's a library, libmpsse, which lets you have kind of Python or C API interface to control the bits that are coming out of this board, which can be really handy as you go into the scenarios where you have these non-standard protocols. Any questions? Oh, come on. There we go. Sorry? Better manufactured than the one from China? Yeah. I would, based on my experience, say probably. When I order stuff in quantity from AliExpress, I expect to get like 10% failures. When I order from Adafruit, if that happens, I just send them back and send the new ones.
How much success have you had using these things against IoT devices?
They're my go-to tools to mess with IoT devices. I prefer these to the more expensive ones, mostly because I've got them, and one thing I do, if I'm dealing with a system and I want to find a serial console on it or JTAG pins and they're hard to find, I would much rather take a $15 board and wire it up once and leave it with that system and never take it apart, then take it off and say, oh, well, it's my $15 board. I'm going to go use it on this board and this board. Because I'll go back to that same board, in a week and have to go spend a half an hour finding those pins again because I'm really bad at documentation. When I could just leave that $15 board attached. Even more so, you can get serial cables that just do UART for like $1 or $2. Like, there's no way that it makes sense to ever disconnect a serial cable once you got it connected and working, in my opinion. And behind you?
So I have a question about analyzing secure hardware. So for example, if the ROM is like, if the flash is read-write protected, can you do there, for example, you could overwrite the shadow code using flash?
So that's where you suddenly get into the next level of complexity, right? The question is like, what happens if you have like a readout protection or stuff like that? So again, that's where you have to find out more about the chip you're targeting. If we're dealing with a spy flash chip, right, that's in a system, and they've done something fancy, like, worst thing you do is you like desolder it from the system and you can read it, right? Unless they're doing fancy stuff like encrypting what's ever on that. Well, if they're doing that, where's the key? Well, it turns out a lot of low-cost systems don't actually have provisions to store their keys inside, so they store them externally. So find out where the key is and read it. Or use a logic analyzer and sniff the key reading mechanism. Basically, everything has to, homomorphic encryption aside, everything eventually has to be decrypted for use. So sit around, listen with that logic analyzer, find out when you can grab the firmware when it's, in plain text. Does that answer part of your question?
Yeah.
Others?
What's your success rate with getting JTAG to actually work on the boards?
That's a tough question because, so when I was doing consulting, like I would be presented with a board and have to get something to work on it. Now that I don't do that anymore and I just teach, I go and I grab a dozen boards and I pick the ones that are easy. So I've gotten really good at picking ones that I know JTAG's going to work on because I want good examples of having them work. So I would guess when it comes to like random selection of like off-the-shelf networking equipment, right? I can't guess. What I am finding is more often devices actually have JTAG disabled in some way, shape, or form. Sometimes that means they didn't put a header on it. Sometimes that means they cut the traces or didn't put traces on it. But even if they did, there's often ways to restore that. Sometimes they actually use bits to prevent JTAG. So actually I was dealing with a PLC and they had an XP LPC microcontroller on it. And that supported code readout protection and JTAG disabling. They didn't use it. So, yeah, whatever. But if they had, you can go down the path of more invasive hardware attacks, glitching, or otherwise messing with the system to get that device to give up its code. Pretty ready for lunch. Everybody's like, if you just stop asking questions, we can eat sooner. Thank you very much for having me. I am delighted to finally make it to Securi-Tay. Please find me, ask me questions. I also have a lot of stickers with me. Did anybody read the big hack, the Bloomberg article? No. About Supermicro having this grain of rice size. Anyway. So, what? I have a bunch of I want to believe stickers. So, come and ask me for those. Thank you again.